These are the solutions for suggested problem set number 4.2 for AP Physics C. These all involve circular motion to some degree. So, question 5.46 has a car that is traveling in a vertical loop, which is a type of problem that we should be aware of. And it says the mass of the car is 8 kilograms, or I'm sorry, 0.8 kilograms, and it travels at a constant speed. And the radius of the track is 5 meters. And then it says the normal force at B, so we'll say that's FNB, is equal to 6 newtons. What is the normal force at A? So, in order to tackle this, I'm going to draw a couple of free body diagrams. So, we'll start with B. So, at point B, we have the force of gravity, of course, pulling down. And we have a normal force also pushing down on the car, because that is where the surface is in relation to the car. So my sum of forces in my only direction here is really not in the y direction, but in the centripetal direction. You can say it's also the y direction, that's fine. Is going to be normal force plus the force of gravity is equal to MAC. And the reason they're both positive is they're both pointing toward the center of the circle. So really I can say Fn plus mg is equal to mv squared over r. So I know all of these things. I know normal force at the top, which is 6. I know mass, I know g, I know radius. I do not know velocity. So what I'm going to do is I'm actually going to solve for v squared. I'm not even going to square root it in this case. So that'll just be r times Fn at B plus mg, and then that's all over m. So if I substitute in for this, I'm going to have 5 times 6 plus 0.8, and we'll use 10 here, so times 10, all over 0.8. And so v squared will be equal to, gives me 57.5. And that would be meters per second, and both of those are squared. So this is my v squared, and so it's a constant speed, which means v squared is also constant. So at the bottom of the track, what's different? Well, at the bottom of the track, I have the force of gravity pulling down, and now I have a normal force that must be going in the upward direction. So my sum of forces at the bottom of the track is again in the centripetal direction, where normal force is positive and the force of gravity is negative, and this must be equal to, again, mv squared over r. So a little simplification, I'm going to be looking for normal force, so I'm going to leave that as is. So minus mg equals mv squared over r. So my normal force will be equal to the sum of mg and mv squared over r. Substitution here will give me that 0.8 times 10 plus 0.8 times my v squared, which is 57.5, over my radius of 5. Then we just plug this into our calculator, and we get a normal force of 17.2 newtons. So, question 5.48. We have a flat, unbanked curve on a highway with a radius of 170 meters. So let's go ahead and just sketch real quick. We have a car coming around a curve that is kind of circular. The radius for this is 170 meters, and they're rounding the curve at a speed of 25 meters per second. So, what minimum coefficient of static friction will prevent sliding? So this is my top-down view. I'm going to now look at it from the side. So I have a car, and there is some radius, 170 meters, and I have some velocity into the page. So I'm turning. So my free body diagram, actually I guess not really from the side, is more from like down here on the bottom. So if this is an eyeball looking up, then this is what I would see. So my free body diagram for this car, if I'm looking at it where the center of the circle is to the right, is going to have a force of friction in toward the right, a force of gravity acting downward, and a normal force acting upward. So, sum of forces for this in my x direction is really my centripetal direction. So I can do x, I can say centripetal either way. If I do centripetal, it makes a little more sense for me, so I'm going to say that the force of friction, which is positive toward the center, is equal to m times my centripetal acceleration. Or I can rewrite this as mu times the coefficient of static friction, as it hints in the question, times the normal force is equal to m times v squared over r. So that's my centripetal force summation. In the y direction, I have normal force minus the force of gravity is equal to mass times acceleration in the y, which is hopefully 0 unless my car sends flying off the road here. So I can rewrite this as Fn minus mg equals 0, or my normal force is equal to mg. So I can take that and plug it into my former equation where I have mu s times mg is equal to mv squared over r. And you see that mass cancels out. So my coefficient of static friction must be v squared over gr. So I can substitute values in for this. So from before I have 25 meters per second squared over, we have g, so we'll just use 10, why not? And our radius is 170 meters. So our coefficient of static friction will be 0.37. So there's our coefficient of static friction. This is part A. Our coefficient of static friction is 0.37. Now, B says, well, now suppose the highway is icy and the coefficient of friction is only 1/3 of what we found. What maximum speed could we have? So, this equation still stands. None of the forces change for my free body diagram, so this derived equation still works. But I'm going to rearrange it for part B. So for part B, I'm going to say mu s times g times r is equal to v squared. So I'm solving for v here. Or I could just say v is equal to the square root of mu s g r. So my mu s is actually going to be 1/3 times 0.37. So I'm going to have 1/3 times 0.37 times, I'm going to stick with the 10, times 170, all square rooted. Plugging this into my calculator, I get a velocity of only 14.5 meters per second. So hopefully you get a smaller velocity because you're on ice, so you should be able to travel only a little bit slower. So, question 50 consists of this interesting giant swing ride at a county fair, and each arm supports a cable that is 5 meters long, that's this cable here, and that arm is fastened to another arm that is 3 meters from the center of the shaft. So A asks us to find the time of one revolution if the cable supporting the seat makes an angle of 30 degrees with the vertical. So I'm going to start with a free body diagram for this person. So my free body diagram will look something like this. Force of gravity going down, and then a tension, even though it's in a rod, up and to the left, and that's it. So this angle right here has to be 30 degrees. So my sum of force equations will look like this. So Fx, or really, in this case, centripetal, which is this way, so this is my centripetal direction, will be just the force of tension component in that direction. So that component is right here. And this would be the other component in the vertical direction. So the force of tension times the sine of 30 degrees, and I'm keeping this positive because this is toward the center of my path, is equal to MAC. Or I can say the tension force sine 30 is equal to mv squared over r. Now in my vertical direction, in my y, I have force tension times the cosine of that angle, 30 degrees, minus the force of gravity is equal to MAY. Now this is 0 because I'm hopefully traveling in a horizontal circle. So I can rewrite this as force of tension times the cosine of 30 degrees minus mg equals 0. Now, what does that mean for us? Well, that means that the force tension is actually equal to mg over the cosine of 30 degrees. So I can pull down my centripetal force equation and substitute and say mg over the cosine of 30 degrees times the sine of 30 degrees is equal to mv squared over r. So mass cancels out here, and this becomes a tangent, and I'm going to solve for velocity here. And the reason I'm going to do that is I'm going to say that the period is equal to 2 pi r over my velocity. Now that came from my circular velocity being the circumference over the period. This is where this equation came from. So I need to find this v, my circular speed. So that becomes, my circular speed will be gr tangent of 30 degrees square rooted. So I'm going to shove that into this equation, and my period would be 2 pi r, I'll use the big R here, over square root of gr tangent 30. Now I could simplify this because I have an r in the top and the bottom, but I'm just going to leave it as is simply because I need to find out r anyway and substitute it. So let's find this r. So the r is going to be this distance here. So it's going to be 3 meters from this arm plus this component of this triangle. So it's going to be 5 times the sine of 30 degrees. So this is my radius. So I have 3 plus 5 times the sine of 30 degrees. Make sure you're in degrees. My radius is actually 5.5 meters. So if I substitute all of this, I have 2 pi times 5.5 over square root of 10 times 5.5 times the tangent of 30, all square rooted. And my period is going to be, with a little calculator magic, 6.13, and that's going to be in seconds. So this is my period. So this is all the work for part A. Now part B asks, does the angle depend on the weight of the passenger for a given rate of revolution? So how do we figure this out? If I were to go back and look at my force equations, what I need to look for is how this angle would be changing depending on v. So in fact, if I look at this equation that I end up with that I can rewrite, so I'm going to say b right here, I have v equals g square root of gr times tangent of 30. Well, what if instead of 30 it's just theta? Hopefully you notice that there is no mass in this equation. Now what does that mean? That means that the angle does not depend on the mass or weight of this person. So question 103 is a calculus-based question related to drag. We have a rock that we are throwing down into water that has some v initial of 3 mg over k. And then k is the coefficient in equation 5.5. So to prevent you from going to look, equation 5.5 is force of friction is equal to kv. So assume the relationship is given by, or between the resistance and speed is given by this equation, and calculate the speed of the rock as a function of time. So we're looking for v as a function of time. So the rock enters water, and then it has this speed function, which is given by some velocity function as time. So we have a downward force, which is the force of gravity, which is equal to mg. And we have the resistance force, which is some friction or drag force, which is kV in the opposite direction. So for convenience sake, we're going to say down is our positive direction. So the sum of forces in the y direction will end up just being mg minus kV equals ma, and then we'll say y. So we have a couple things that we want to do. First off, we know that because there is a resistance force, eventually we will get to a terminal velocity. So v will eventually be equal to v terminal. And when does that happen? That means that acceleration is 0. So that would be the case where mg minus kvt is equal to 0. So if we solve for v terminal, that would be at mg over k. Now, for our actual sum of forces, the acceleration is not 0. So until we get to this point, acceleration is not 0. So we actually write this as a differential equation. So mg minus kv equals m times dv dt, because acceleration is the derivative of velocity with respect to time. So this is a separable differential equation, which means we're going to separate it into the velocities and the times, one on each side. And before we do that, we're actually going to simplify it a little bit. So the first thing we're going to do is we're going to divide everything by k, so that we end up with mg over k minus v equals m over k dv dt. I'm going to zoom in a little bit so that we have a very tight view of this. And we also see that in this particular case that vt shows up right here as mg over k. So we actually have vt minus v equals m over k dv dt. So the next part, we don't necessarily want to work with a negative v when we go to integrate, so we're actually going to multiply everything through by a negative 1. So we have v minus v terminal equals negative m over k dv dt. Now we're going to start separating it. So I'm going to multiply both sides by negative k over m. So it becomes this function. And now I'm going to multiply by dt, at the same time dividing by this set in parentheses here. So what we end up with is negative k over m dt is equal to dv over v minus vt. So now we've separated these two equations, or separated these two variables rather, and we're going to integrate. So moving to integrate, we have the integral on the left of negative k over m with respect to t, and on the right, the integral of 1 over v minus v terminal dv. So I can pull the negative k over m out because those are constants, and I just have the integral from 0 to some time of dt. On the right, I can't make any simplifications. I have the integral from v initial, which is not 0, to some final v. And then that's going to be of 1 over v minus v terminal dv. So this part right here, you should be able to get to no problem. Now, to solve for the function of velocity with respect to time, we're going to integrate. So the left-hand side just becomes negative k over m times t, because the integral of dt is just t, and it's evaluated at 0 and t, which just ends up being t in the end. On the right-hand side, we have the ln of v minus vt. And this is going to be evaluated at v0 and v. So the left-hand side, as we said, just becomes negative k over mt. The right-hand side is going to be the ln of, we're plugging in v, so the upper bound, for v, so it's just v minus v terminal, minus v initial for the same thing. So we have ln of v initial minus v terminal. So I'm just going to work with the right-hand side for a moment. So because I'm subtracting two logs with the same base, I can rewrite this as the ln of v minus v terminal over v naught minus v terminal. So this looks a little ugly, but we can make a little simplification. So if you recall, we said that v terminal is mg over k, and we were also given that v initial is 3mg over k. Therefore, v initial minus v terminal would be equal to 2mg over k, or just 2 times v terminal. So I take this back and rewrite it as ln of simply v minus v terminal over 2 times v terminal. And that's equal to negative k over m times t. So at this point, I can just take both as a power of e, and I end up with e to the negative k over m times t equals, and on the right, I can simplify this a little bit. I have v over 2 times vt minus 1/2. So this is a little bad. What we want to do is we want to clear these fractions really quick, so we'll multiply everything by 2. We end up with 2 times e to the negative k over mt, which is equal to v over vt minus 1. So now we're just solving for v at this point. So I'll add 1 to both sides and then multiply both sides by vt. So my v, my velocity, is going to be vt times 1 plus 2e to the negative k over m times t. And this is actually our velocity function that we're looking for in the end. So if you don't believe me, we can actually plug in some numbers and see, just to double check. So v of 0, if we plug this in, is going to be vt times 1 plus 2e to the negative k over m times 0. So if I plug in a 0 here, e to the 0 is 1, means that this is just going to be vt times 3. Well, since vt is mg over k, that means that we actually have 3mg over k, which is exactly what we thought we should have for v initial. Similarly, if we were to plug in an infinite time, this second term would just vanish and we would be left with just mg over k. So if we really wanted an equation for v in terms of all of the constants given, we should have mg over k times 1 plus 2e to the negative k over m times t. So this is really our final answer.